Good afternoon. I'm glad you're here at this final session of the day. After this, it's a reception and a party. But we'll spend some time together reminiscing on ancient times, looking at old game consoles, the 8-bit era, so that's a while back. And just to get a bit of a feel of the room, because I see a lot of diversity here. Who has played with 8-bit game consoles for real? All right, very nice. So we'll talk about game emulation and how you can use .NET to emulate those things. There's an agenda. Let's see. Just a second. Let me get rid of this. All right. There we go. Put this on. So that's interesting. It might be the video, could it be? Let me check. All right, that looks better. All right, okay. Some glitches, it happens. So we'll talk about retro gaming just to set the scene, but we do want to look at the inner workings of 8-bit consoles and processors in particular, because if we want to emulate those, we sort of need a deeper understanding on how these machines work. So we'll spend some time there, and then we'll start talking about how would you emulate these, and what does it take to implement that in a language, and particularly in a managed language like C#, using the .NET framework. So that's where we will spend the majority of the time. And also a slight thing there is the game framework to start visualizing things, because when we're just doing C#, we can do a lot of emulation, but we need to visualize things and we need to make some audio audible. So that's where we need a little bit of help of additional frameworks. And I'll show you a approach, not the only approach. All right. So emulators. I'm assuming that some of you have used emulators before, just to run it on your laptop or on your gaming rig that you have. And you might even have been running this on existing consoles, because even the big consoles like Xbox or PlayStation, they do use emulation to run older versions of games on newer hardware. So you will probably have used it before. It's kind of comparable to virtualization, because you want to have the programs, which is a set of bytes stored somewhere. You want to have those running in sort of a player or executable that plays through it, like those machines you see on the street, the organs where you put it in the cards and it just plays the cards by looking at the punched holes and making all the particular noises. So that's the emulation. Why would you do that? Well, way back, they sometimes built emulators because they didn't have the hardware yet, so they could get started on building something, even though they couldn't physically test it on a device. It's also a way to continue development for old systems, and especially if you do homebrew development, because that's happening more and more now, since these games are usually sort of end of life by the respective owners, like Nintendo, Atari, Sega. People can still work with it, but it's much easier in your development cycle if you have an emulator. Also, and I like this one as well, there were a lot of games when I was playing the real thing that I couldn't finish because they were just too hard. And at some point in the game, you would lose your lives, and then it was game over, and you had to start all over again. There was no save state in most of those devices because they didn't have any storage. Later versions sometimes had EEPROMs, so they could write a little bit of state somewhere, or you could have some continuation code or a level code, but sometimes it was difficult. But with the emulators, you can just create a save point, restore state, and continue just before you lost your last life. So that's kind of a cool thing. Now, why did I do it? Well, my very first game thing was an Atari 2600. We got it in our home, and I played Asteroids and Pac-Man with all the flickering Ghost and all in it. That's what my first thing was. So that was I shifted to Atari instead of Nintendo. And as a student, when I started studying, the Atari Lynx came along, and it was like a handheld console you could carry along. It had color graphics, it had a very big appeal. The Game Boy was there, but the Game Boy was just sort of black and white, 4-color grays. So I fell in love with the Atari Lynx, and I've been, working with that ever since 1989. I bought mine in 1990, so that's quite a while ago. And I wanted to know, can I build an emulator? And I had some spare time. Back in the day, I had some spare time, not anymore. And I wanted to learn the inner workings of a game console. And I'm not an electronics guy, but still, you can get really far. And it was something different from building business logic in a web application. All right, so a couple of things here. The TV sets are the ones that you connected to a television set, and you needed RF output, with the exception of the Vectrex, the right one, which had its own little tube where you could play vectorized games. You have the ones with keyboards, and you have, well, some of the more common handheld game consoles. So I'm wondering, does anyone in the room not see their go-to thing that you had back in the days? Which one was that?
Master System.
All right, the Master System, yeah.
Is it basically the Game Gear, but plenty of TV?
I think there's the top left one is the Japanese version of it, or?
Master System 1,
Yeah.
the other two.
All right, okay. So you were, I believe, the only hand that was there. So this is pretty good wrap-up of all the things. I'll be looking at the bottom one, and in particular the Atari Lynx, like I mentioned. But what I show you today, we'll go for just about anything. All right. So just going quickly through this, what makes 8-bit games so typical? It's the graphic style. Usually the devices have very low resolution, so you had to work with limitations in color, in how much you can get on a screen. But still, the game characters are pretty iconic. And they were able to build really cool games. That's the Pac-Man I mentioned with all the flickering ghosts, because it can only show one ghost at a time, so they alternated, and was an epilepsy warning was in order there. And then you see arcade games, which were also using the 8-bit processors underneath. And I like, for example, the Sonic the Hedgehog, which was a Sega Master System or a Game Gear version, which had really, really cool graphics, but it was still the same type of processor, but they just learned how to better utilize the things. Now, I'm going to click things again and not hopefully lose the screen. I'm not sure if there's any sound. Oh, well, there's not even sound hooked up, so let me just skip that. There we go. Yeah. Oh, the emulator crashed, yeah. Could have been. No sound, but you probably know the chip tunes, the Commodore 64 music. It's pretty well known, and it's being used by people all over, well, not all over the industry, but a lot of music has influences of this 8-bit typical sounds that they just put in there. But that's just, that was that era. And I used to record tapes on my, to play my Walkman and just have the music of demos that they had, like Rob Hubbard, for example. He was one of the guys that made really cool music, play that. So reminiscing. 8-bit architecture. This is a architecture that is pretty common in that era. It had a central processing unit, CPU, or the processor. And usually they had a bit of ROM that was executing code during startup. It had RAM to work with, mostly very limited. 64 kilobyte was usually the limit that they had. And then there was some I/O and other devices. So it might be keyboard, might be joystick, but might also be things like timers, which are also considered other things. And some of the consoles also had some form of serial communication via UART. So that's kind of what they do. They need each other. Not all of them need everything, but for example, the CPU needs to access both ROM and RAM, but other devices might also need access to the RAM. and only one can do that at the time. So they have this bus structure, and the bus transmits 8-bit data, which is logical because it's an 8-bit processor, but the address space is 16-bit. So 16-bit evaluates to 64 kilobytes of possible values, meaning 64 Ks of bytes that you can address by specifying that. An 8-bit control bus is, well, some form of how big the control bus itself is. But only two can use it at a time, so there is some arbitration going on, who gets to talk to who, and usually it's the bus controller that takes care of that. All right, so they all talk to the bus, never directly to each other, so the bus can take care of the communication. All right, so remember this picture because this is pretty typical, and this will reappear inside of the emulator later on. Now, which processors are there? The Z80 was a pretty popular one. There were a lot of consoles that use it, a lot of arcade machines as well. So, for example, Donkey Kong used the Z80. And then you have the 6502 family, which was a cheaper version, and it comes in a variety of generations. Pretty well known, the 6510, the 6510, is the one that was being used in the Commodore 64. And you have the 6809, that was pretty well known because of the Vectrex. But these are things, you know, and they have a frequency at which the execution of instructions is being done somewhere around 1 to 4 megahertz. Compare that to gigahertz frequencies on your laptop now or your other devices. So there's a big difference, but this is what kind of saves us, because if you need to do a lot of calculated things with emulation, if the frequency of how fast you should execute your instructions of what you emulate, you need to keep up with real time. So this is kind of good that it doesn't go too far. The other thing, memory. Memory, like I said, is mostly 16-bit address space, so that's where you can get these hex numbers. The $, if you're not familiar with it, is where they say this is hex values. So this entire range of 16 bits, which means 2 bytes, gives you 64 kilobytes of RAM. But the RAM, this is just an example, is divided into certain areas in most devices. So some memory areas have specific needs. Sometimes they have ROM-mapped memory inside of RAM. So you pick an address, but you actually end up on the ROM, which might be the cartridge that you insert. And there might even be things, and we'll talk about that, where addresses in RAM are actually evaluating hardware behind it. So those are memory-mapped registers, where you can talk to RAM memory, sort of, kind of, but it means that you're switching things in the hardware or starting operations in the hardware. And sometimes memory is mirrored, but that usually means that some of the bits in the address don't really matter. So you'll find that the things seem to appear somewhere else, but it's just that some of those bits don't really matter. And that's something that if you build your emulator, you need to be familiar with. If I pick an address, where will I end up in the memory map? And this is usually refers to as just that, a map of the certain areas. Now, inside of an 8-bit CPU, you'll find that there's certain areas. One of the things is the crystal. And the crystal has ticks, like a clock that ticks. It ticks at a certain frequency. Sometimes they call them cycles, but if you're very official about it, it just is a alternating signal that goes up and down. So it's like a square wave that makes sure that things are being iterated. And it's driving these things with the phi1 and the phi2 in and out. That is what under the hood is pushing your CPU to do things. And the CPU will follow the rhythm of the crystal. And most of the time it's that a single crystal tick is also a cycle inside of the computer, inside of the CPU. What it does is, it has quite an elaborate mechanism to do certain cycles within an instruction. So if you say, for example, I want to write a value to memory, it first needs to read the actual instruction that does so. So the opcodes are the instructions, and they need some input. Think of it as function names with the arguments that you pass to it. And then you need some internal memory, because you need to keep track of things, some state. you have registers, and this is different for different processors, but the 6502 has an A, X, and Y register. And the X and Y are for indexing, and A, the accumulator, is used for storing just a temporary value. And you can work with memory, but memory access is reasonably slow, so you see a lot of code back in those games just pushing things around from A to X to Y and back into memory doing calculations. Very simplistic because there wasn't a lot that these processors could do, but still you could build games. It has status flags. So for example, if you do a subtraction, you can later on check if the value is null, 0. And that means that the flag for 0 has not been set, or has been set in case of 0. And it has a negative flag, it has a carry flag, and depending on your processor, there are certain flags where you can see what the effect of operations was. And again, depending on which one you have, might have dedicated stack. And the stack, just to know where you push things and pull things, is in the 6502 is an area that is 256 bytes. So that's it. That's the special area inside of the memory at the beginning, and you can have it grow, but there's no checking, so you can overflow the stack just by pushing on too much, and there won't be much that will help you. Will overwrite your own memory, which essentially means overriding your own program code. One other thing that's important, because as soon as a CPU starts executing code and just starts reading memory, it will be in a sort of infinite occupied by executing that code. But you do want to know when some things happen from the outside. So that's where interrupt requests come in. And from the outside, a peripheral device like I/O, incoming I/O, we've got a new byte over UART, or a joystick that is being pressed and needs to be read and pushed in. You want to interrupt the processor. And that's what the IRQ does, an interrupt request. And that will have the CPU say, okay, I now need to look at a special code. It's like an event handler. It reads the address of that particular code and then jumps there and starts executing there, the code that is there. That's an interrupt service routine. And then you can do whatever you need to do. Sometimes it's related to video, like for example, reaching the end of a line. You want to change colors, so the next line has different colors, or you can make nice gradients or something. So those things are IRQs, and NMIs are non-maskable interrupts. So essentially the same, but an interrupt can be suppressed by saying, I will put the interrupt disable flag to true, one of those flags that we talked about. And if you have that set, an interrupt request will be ignored because we don't want to be disturbed. But the non-maskable one is the one that will always push through and start executing something. So it's not often used, but it's something where you can't delay or ignore what is happening there. Interrupt sequence, a bit detailed, but so I'll be brief. But the idea is that this interrupt service routine is being loaded from a well-known place inside of the CPU. I put the addresses up there. So for an IRQ, it's the second to last and the first to last and the last address of the address space. And those 2 bytes are the address of where your code is that should be executed. And it will do some preparation, push the things on the stack of remembering where it was before the interrupt, go fetch the interrupt address, execute the code there, and return by getting things from the stack again. All right, so who has looked at this assembly code before? Well, okay, about half the room. All right, so just to go through it, because if you build an emulator, this is most likely what you'll spend most of your time on, that you want to be able to look into memories, the addresses that are there, and then you have your instructions there. Different processes, different instruction set. This is for the 6502, and you'll see that the first green column is the instruction itself. So the top one is load accumulator, and it loads an immediate value, so an exact constant value that is hash $77, and then it stores the accumulator in the 0-page address 0B. So you don't have to understand all this, but there's logic to this. But you see the instruction and then the operand that is behind it, and those need to be fetched from memory. The last column is the expression of what were the bytes. Those carried meaning, but the mnemonics, that LDA, are for developers to know, so they don't have to know all the codes by heart. So LDA is something that we need to implement later on, and we know that the next thing in the address space is the value that we need to put in this A register. So it's very simplistic. If you look at it, you can already see how you would do this in C#. Have a field with A and then load something from an array, 77, and put it in there, and then that's this thing emulated. All right, Atari Lynx. Who had an Atari Lynx? One person in the back. Okay, I had one too. So this is just to have an example and talk about something specific. The handheld device, like I said, was 1989, so it's already almost 37 years old. Was a big competitor to Game Boy, Game Gear. It lost the big battle. Game Boy came out as the winner. So Atari went bankrupt. They stopped development of this, and there were only 70 games released. So if you're a collector, it's a really easy way to get your complete collection, because there were only 70 commercial games. There's a very active community now that's still building games, so I think that the number of games is now well over 200 or something. Some of them have been published, some have been put out as just binary images, and that's where you need an emulator or a cartridge that you can put the binary on and then load it in an actual device. The most important thing here about the technical specification is that it has a 6502 processor, but a more modern one. CMOS, so no longer NMOS, which was an older technology, but CMOS with the SC and the C that are in between the 6502, meaning that they have a little bit more instruction set, and some of the hardware bugs inside of the old 6502 were fixed there. Other thing is, so besides the CPU, which had some additional things added to it, there was also a math coprocessor and hardware accelerated graphics inside of a custom chip called SUSY. And the chip that is the 6502 had timers in there as well, and that was called Mikey. So Atari had a lot of those things where they had nice names for the CPUs that they used. You can see them here. So those two are SUSY and Mikey. Later on they named it Hayato. I've no clue why they did that, and then it became the CO2 instead of the SCO2. But this is the Atari Lynx 2. So the pictures that you've seen is mostly Atari Lynx 2. It has a RAM memory. These are RAM memories that have a nibble each. So a nibble is like 4 bits. You have 2 nibbles to a byte. So they store half of the bytes in each of those areas. And you can see the oscillator that's 16 megahertz. So it's pretty fast, much more than the 4 megahertz. But this is, once you get down to how fast does the CPU tick, it's sort of divided by 4. So that it runs at about 4 megahertz. You have additional hardware, like shift registers that shift bits around, but that's mostly for reading from a cartridge. They originally had the idea that the handheld would have a tape cassette, so they could put tapes in there and like a Commodore 64 loaded from there, but they skipped from it, but they still have the logic to sequentially read through a cartridge, page by page. And just so the shift registers are just by shifting the bits, so you go through it sequentially. All right, emulation. What do you need? So now we know a little bit about what is the hardware about. What do we need to start building an emulator? So first of all, it would really help if you have a different machine that wasn't listed here, if you have documentation. The Atari Lynx had a very thick binder with all the documentation. It's been scanned, it's available on the internet, so that was a very thankful source of what do things mean, what are the internals of the hardware. The other thing is, if you start using it and you have a boot ROM, for example, you will need access to the boot ROM. That's what you'll need to extract from a console, and probably it's already out there, but you do need to check if you can distribute those things, because sometimes it's part of the hardware and it's copyrighted, even though it's very old. And also, it helps if you have the actual hardware and can look at those things. You can hook up logic analyzers, for example, and look at the real signals that go through the clock and through memory access, the address bus that is being utilized. So that's helpful. And obviously, you know, probably if you start building an emulator, it would help if you have some connection, like passion for the device, like I did. Then you need to choose how will I emulate. And there's a couple of ways to do it. What I've been walking through it, like looking at the assembly code and looking at the bytes and explaining what each of those instructions does. That's the first one, interpretation. Just interpreting the program code and start executing it. That is easy because some of those games had self-modifying code. They would overwrite pieces of code by switching, for example, if you should jump to a certain address, but changing the address dynamically. So they would change the code. So if you do static translation, you would need to look up front at all the code and then translate that to a different language. Doable, but if the code starts modifying itself, you wouldn't have that in a static translation, right? You could do dynamic translation, but that's kind of difficult because you need to see when code is being changed and then re-evaluate things. So doable, but difficult. And the high-level emulation is where you start using the native hardware to run old hardware as on the new hardware. So that's kind of where it still runs without any translation. We'll be looking at this one, the interpretation. Now the main emulator loop is kind of, you know, with in pseudocode, you enter this infinite loop that can be interrupted by, you know, exiting the program or pressing a special key or whatever. But usually you start with, we execute a number of instructions. On the circumstance, it can be more than just one, but typically it might just be one instruction at a time and go through that. Once you've done one instruction, you need to check, did we get interrupted? So we generate interrupts and look if we need to be interrupted. And then we go through emulating the graphics. So there's memory, and the memory translates to video memory, for example, and we need to build like a bitmap or some form of visible screen. Same with the sound. The sound is being dynamically generated, so there's no modern game development, for example, has assets that they use and display those assets. Typically here you just change the waveform of what you have. And then finally, synchronizing time is mostly needed because if you start calculating what a CPU does, it will do it much faster if you can keep up than actual time. So you need sometimes to wait a little bit for real time to catch up with how fast you executed an instruction, probably faster than what the original CPU did. The emulating other hardware is where you do things that are outside of the processor and that you need to do, for example, serial communication or reading joystick or keyboard state. This is where we go, how I approach this. I thought, okay, let's make an abstract class processor base that captures the shape of a processor. Could be used for, I think, many processors, because I think that they usually start with initialization. That's during startup when the power comes on. Then the execution, the signaling of an interrupt, which could be the maskable or non-maskable one. And most of the time, these things we're able to look at a certain key press or a signal going high on a line where it would do a full reset. And then it would still be powered on, but it would go through a reset cycle. And the other things that are listed there are the internals that we talked about, the A, X, and Y registers. But there's also the stack pointer that points into the stack where we're currently at. And processor status is the flags that we have. And you have a current program counter, which is where are we in the memory that shows the A977, you know, the current instruction that we need to execute. So that's kind of the outline of having the moving parts inside of the processor. And this is what you need to work with and then start doing all the code. One other thing, if you do an execution, this interrupt thing is pretty prominent because it's an important deviation of the normal flow. So some of the processors are also be able to put into sleep, because back then you would have batteries, for example. So if they could put the processor to sleep while something else was using the bus and accessing the memory, then you would use less batteries and you would have longer battery life. One of the reasons that the Atari Lynx lost the battle is that it needed 6 AA batteries, and like 3 hours in, they would be empty. So, you know, and the Game Boy fit in your pocket, only had 4 batteries, and you could do almost a full day playing those batteries. So that's where parents said, well, we'll get the Game Boy. So, you know, it does matter. But the 6502 can be put to sleep, can be woken up by an interrupt, and this is kind of what you see, that if there's a system IRQ active, we wake the CPU because that is built in, and then we just check, can we run the interrupt sequence? And sometimes, you know, you see the non-maskable one makes it go through, or if the interrupt disable flag is not set, then, and you have an interrupt request, IRQ, then we need to run this complex sequence of things before we go into the service routine. And the other thing that we go through, and I will demo it in a bit, is that we go through fetch the opcode by looking into the memory and deciding what to do next. Yeah, so I think we're at that part now. All right. Now I need to pay attention because if I switch out, I lose the screen. So there we go. All right. So quick overview of what I have. This is the Atari Lynx emulator. It's on GitHub. You can look at it. The links are at the end. And the way I set it up is that I have processors here. So this is the processors where it contains 6502 and the 65C02. Those two are in there. It also has EEPROMs, but we won't go into that, but that's programmable chips for storing things. We have the Atari specific stuff, and this is where we see audio cartridge, the Mikey and Susie chips details, the UART for serial communication, and the rest is, you know, what makes a Lynx. And the Lynx uses the CPU and the other hardware that needs to be emulated. So that emulation code is here. But we'll first focus on this here, and we'll go into the NMOS, which implements processor base, which is the thing with the execute code and everything. It has what we saw before, these things here. So it has the registers, the program counter, and this is where we'll get into what do you need to do this in .NET. Do a lot of bit manipulation, because using flags, the flags are bits inside of a byte. So you need to start flipping bits of that byte by doing ORs and ANDs and exclusive ORs. So that's what you'll see here is shifting from bits into member states, like this N, V, the negative, overflow, the break, this decimal, interrupt disable, 0 and carry flag. Those are all deductible from the individual flags, the bits inside of a byte. And this will reoccur when we start talking about you know, how a CPU works with hardware and how it works internally. Let's see if we start debugging. We can see a bit of the flow. So of course there's a lot of bootstrapping going on, you know, that we need to assemble all the moving parts like Mikey, Susie, RAM memory. We all need to pack that together into a single composition of objects. It has a well-known boot sequence, but where we end up is that we start executing those cycles, the instructions that are there. So let's just step through this. So we have a cycle count. We need to keep track of time, and keeping track of time means you need to look at how many cycles did the crystal tick or actual cycles that were being executed, because that gives us the best indication of how much time we've spent by executing these things. I'll get rid of these, so we have a little bit more real estate. What you also see is that I've documented it as best as I could. And everything that's in the quotes is official documentation, either from the processor or the Atari Lynx or your emulator that you want to write for the device, because it shows you why certain things are in the code, because it's there for a reason, and you don't just make up things. You try to mimic the hardware and the behavior as best as you can, and that's where I found it helpful to say the interrupt signal waits for blah, 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 and then you can do the implementation. So we looked at an abbreviated version of these things. But here we go into, let me just go over here. We look at the memory. We look into memory, and you probably heard about peek and poke. Poke is writing, peek is looking. There's even a nice comic that's called Peek and Poke. Look it up, it's very funny. But the peek is, okay, look at the program counter, which is a pointer somewhere into memory, and that's almost as the yellow thing for the debug breakpoint that we now have. That's where we are. That's where we'll read the opcode. So if we do that, we can look at the opcode, and it's 173. If you switch here and do, let me see, hexadecimal display, you can see that it's 80. And 80 is an instruction that you can look up in the large instruction sheet, but we'll get to that in a bit. Each of those instructions takes an amount of time. Simple ones just take a few cycles. Some take up to 8. The shortest one or 2. And we know that from a table, so we can look at the clock. We increase the program counter because we've just read a byte, so we now need to look at the second green column that we saw before. And then we need to execute the opcode. We now know which one it is, so let's jump into that one. And then we need to do a switch. In the meantime, you've seen that we've ended up in a new class. This is a choice I made. I used a subclass of NMOS, that's the CMOS SCO2. So it's a choice how you would do that, but they are mostly the same, except that there's some behavior in the CMOS that overrides or is different from the other one, and some additional instructions that were added to the newer processor, the SCO2. Anyway, so the table, the large switch statement here is all the instructions that exist for this processor. The NMOS has a similar table, but it's a slightly shorter one. There's other gaps in the implementation. So if we switch to the opcode, apparently the instructions that we had wasn't a load accumulator, but not this actual value 77, but it's an absolute one. So they say load the value of some other address. So it's like looking somewhere else and getting that value and putting it into A. So to get the absolute value, we need to look in the memory and then get not just a single byte, but 2 bytes where we need to deduce what is the address that is coming from there. If we look into the memory, let's see if we can, it will be really hard to look into that one, but the memory there, so the 8-1 is the first byte, and then the next byte we read as well, and that will give us the address. So the address that we need to read is FC88. We've just read 2 bytes, so the program counter needs to be advanced 2 more. So we're at the next instruction now. Now with this address set, we can jump into this load accumulator. It will now load the data that is at that address location. It could have been the program counter with 77. It would just be the program counter, but we've just read somewhere else. It's loaded into the data. And then we can push this data, like 0-1, we can put it into the accumulator. And then update the flags, because the effect of setting a value in the accumulator is that they will update the negative and 0 flags. So the 0 flags are, you know, that's the 8th bit in the processor status. And if that this byte value has that value set, so it's 0-1, that doesn't have the first, so the most important byte set, meaning that the negative value will be false. And the other one, the zero flag is if the value of the accumulator is 0, so the zero flag is also false because it's not set. And then we go back to, if you read the processor status, it did all the ORs of the individual flags, and we get the value from the processor status. All right, so that's been set, and then we end up here, we're done. We go back, we say, okay, that's been done. We can now compute the number of cycles that have been done. We started at 0, obviously. We took 10 cycles, and then we go back to the top again. And we execute a new single instruction, and that's the main processor loop. Make sense? All right, very nice. So, yeah, there we go. Now, I've sort of skimmed over that it was just reading memory, right? But mostly with this memory map, there were different areas. Some areas were actual RAM, some were ROM, some were mapped to hardware. So I chose to do an interface that says, okay, you have memory access, you give it an address, a certain type. That will be a U-short. U-short is 2 bytes, so that's exact match to the 64 kilobyte. And you get back a shape of data, which is byte. So in general, mostly you will have iMemory access of U-short to byte. Peek and poke, and this is the thing that must be implemented by something that works with memory or represents memory. So for example, this class RAM 64 kilobyte memory implements the U-short byte for iMemory access. You can sort of think of what the RAM memory is like. It's underneath, if the pure RAM memory is just an array of 64 kilobytes of bytes. So that's the thing. But we need to do smarter things to make that work. And I also wanted to show you a couple of things. If you're doing C#, and I wrote the initial version in 2010 or something with a very early version of .NET. Well, at least not .NET Core and onwards. This was the initial implementation of the memory access, just a simple byte, and we could read into it. So if you wanted to do a peek, you would do something as simple as this. You didn't have the lambda-like arrow yet, but this is what you would typically do. And this works fine, but if you notice that the memory access in this way in larger arrays becomes very, very critical in terms of performance and penalties that you have, you might take a different approach. And that's possible now with .NET because they know that sometimes you want to be faster than that. Indexing into this large array, and the larger it becomes, if you do maybe a 16-bit emulator, the more expensive that becomes, is because they do boundary checks. Don't you go over the length of the array? And that's what that you'll get memory, or you'll get exceptions. But you can say, I know what I'm doing, and just don't do the boundary checks. And that's where you can do things like, well, then it becomes a bit more, a different approach. You take the RAM, you say, give me an array data reference. So that's sort of the value, the starting value in .NET where it's raw memory instead of managed pointers and stuff. And then you say, I want to do an unsafe add because I know what I'm doing, and I want to add the address. Why are we safe here? Because in the construction of memory, we check that it's exactly 64 kilobytes, and the U-short address can never exceed the bounds because it can't contain a value that's outside of the bounds. So we're pretty safe there. Then you can decide, and I put it in just because this is what you typically don't see, the 2 ref words at the beginning. This means that if you get back the byte that is located at that index in the array, the ref means that you have the actual value, not a copy of. And if you change that, so the ref byte that you return from this, if you would change its value, it's actually doing a poke. So you might also leave that out, so remove the first 2 refs, then it's just a copy of the value inside, but it's a value type, it's just really only allocated on your stack, so pretty fast and not much overhead. All right. Now we get to the point, the CPU it's just a off-the-shelf thing that they bought. The 6502 was pretty inexpensive, so they could buy them for $20 or something. So that was really, really cheap, but it was just executing these instructions. It had no idea of what you would build around it in a computer or in a gaming console. The CPU only sees RAM. So if you do a poke to a certain address, FC80, and you put the value D5 there, the CPU doesn't know any better than I'm writing to RAM, I'm just doing a poke. And that's it, I'm done. Store accumulator in that address is probably the real instruction that you would use in 6502 language. But that means that you can only use RAM, and you want to communicate with the hardware as well. For example, read joystick state. If somebody pushes buttons, you want to know which buttons have been pushed. How does that get into memory? Well, that's where they do two things in the consoles. So first of all, they have some form of memory map unit. And the memory map unit looks at certain flags that have been set. What do you want to see? Or which area of the address space is this? And it might be ROM, it might be cartridge, and it might be hardware. And that's the electronic implementation inside of the console. And we need to mimic that behavior as well. So the Atari Lynx has the first 62 kilobytes all as normal RAM. It's the last, well, it's actually the last 4 kilobytes that are different. 2 kilobytes of ROM and 2 individual bytes of memory space that is allocated to Mikey and Susie to work with the hardware that's located inside of those chips. Those are called memory mapped registers, and that's where I think things get sort of interesting, because in this case, Susie, for example, might have at that location FC80, documentation is what you need. It might have a certain meaning if you put a value in that register, and in the next slide we'll go into that. But from the CPU perspective, we're just writing a byte of data. You see the little highlighted box? That's what we're doing from that side. But the other side looks at it per pixel, per bit, so to speak, because it means things. And the emulation logic needs to look into the individual properties that help you evaluate the particular bits inside of that byte that we just wrote. Let me explain. So the bits inside of a byte, they sometimes work as flip switches. Turning a bit on means you do direct memory access or sequential memory access, depending on how you flip it. It might also be settings. I want to have so many colors per pixel to have a bigger or smaller palette that we can use for a game. So this poke that we talked about, you need the documentation. And in this documentation, it clearly specifies each of the meaning of each of those bits. And the ones that we'll be looking at is bit 7 and 6. But here we can see it a bit better. So I've laid out the byte, the most significant bit, bit 7 at the top. The top 2 Bs are the bits per pixel. That is a number that indicates, 2 bits can be 0, 1, 2, 3. You add 1, so it's 1, 2, 3, 4, and that's the number of bits per pixel. So that gives you either 1 bit for color, 2 colors, or 4 bits, meaning 16 colors. And then the H flip, V flip, those are underneath. They are indicating, should a sprite be flipped, like so, or both. If you write D5 and you look at the individual things, so the D is the top nibble. D is 1101, the top box that appeared. So that kind of says, we are writing 3 into the bits per pixel, but we need to add 1. So that means we've got 4 bits per pixel. The H bit is not set, so we have no horizontal flip, but the other one does have flip. So you kind of see, for this example, what the meaning of a byte inside of a memory mapped register is. And the hardware on the other side looks at the individual things, and there's lines connected to it that look at if something is high, it will activate a piece of hardware or not. So that's electronics again. manipulating those values, writing the entire byte value, that's quite easy. But what if we have some emulator logic that says, oh, okay, in this case, we need to set the V flip to on, because that's what we need in our logic. Then you need to make sure that the vertical flip gets the 1-bit set on bit 4. So typically you would use a mask, which has the single bit you want to manipulate. And then you just do an OR with the value that you have. It will stay the same, but we know guaranteed that the 4th bit will be a 1. Alternatively, sometimes you need to flip it off. How would you do that? So then you need to take the XORed value, flipping all the bits, so every 0 becomes a 1 and a 1 becomes a 0. And then you can do an AND with the original value. And that means that everything stays the same except the 4th bit, because the 4th bit has a 0, and an AND with a 0 is always a 0. So you know that you turn off that particular bit. In code, it would be something like this. You see the byte data at the top. That's the complete byte that's being written by the CPU. Doesn't have any clue what it means. Our implementation of the emulator logic for the hardware, it's much easier if we have properties indicating the individual bits, so your code becomes more readable. So the V flip, you can see, in the get, you see that we check if the V flip mask is the bit on, just by doing an AND and seeing, do we get the same value back? And the other one, if the byte value and then the ternary operator value does it need to be on or off in the setter, then we can do either the OR with the mask or the AND with the XORed value. And then the bits per pixel, different approach. Another thing that you'll be doing if you write emulators is just shifting bits around with the bigger than, or smaller than, just shifting bits a number of positions, in this case 6, so we're shifting the most important ones, we're shifting it all the way to the beginning, and then we add the 1 to get the bits per pixel. Once you start working with this and doing all these things, I encountered, and look at the picture, there's weird yellow lines that shouldn't be there if you know the game. It's Dirty Larry, Renegade Cop. The yellow thing shouldn't be there, and I was wondering how, what? And it turns out to be a bug in the bit operation. So I made a mistake with one of the flags, but because I didn't have it covered with a unit test, I didn't find out until reasonably late. And debugging an emulator where you do millions of cycles before you in the game encounter the position that something in video memory gets corrupted is really, really hard. But I eventually found it, and then I was encouraged to do even more unit tests. And we'll look at a bit of unit testing now. All right. So let's quit this. Go to the tests here. So for example, this is a typical test that you might have. So this arithmetic shift left shifts bits to the left if you, and they look at either the accumulator or at an address. But you can imagine that if you're shifting bits, and I need to think about how you're seeing it. Yeah, so it's shifting to the left. The last bit might fall off. And the last bit, if it falls off, it gets put into the carry flag. So we remember, okay, we've got one left, and then some on other shift operations, the next one we can shift it back in. So we're shifting across bytes. That's kind of the program that you did. So in this case, it's an ASL8 with the accumulator. We put the instructions in. It's a single byte instruction. We initialize the memory with this instruction. We say execute it, and then we assert, have the right things been done? Because we know the effect of such an operation, and we just, for each and every situation, we can go through all of these. I wasn't super complete with this, because it's quite a number of situations that you have, but I picked the most important ones, or the ones that I ran into. But I also looked at this functional test thing, which is if you look for your particular device with the processor that it has. Probably there's someone that wrote a test suite, and in this case, if we scroll down a little bit, it displays here, this is where the code starts, that starts exercising the CPU, and the thing that we run is we load the file, we put that into memory, we copy the entire thing in, we put the start value at 0400, which is this address here, so this is where we start, and then we just say start executing these 3 million cycles. And the program is written in such a way that only if you reach the end up at this location with this value in the accumulator, that all the instructions of the processor will have passed the test. So this is just a massive test of the entire processor, and it's quite fast. We might give it a spin. Let me see. Functional tests. It passed 1.7 seconds, but it did 3 million iterations on the processor, and it all went according to plan. So kind of a bigger test, super test on top of the other things. All right, so be mindful of time. Let's go through the next thing. I'll be brief here. So video memory is the typical for your type of device. In this case, it's all this manipulation of individual bits. This is the bits per pixel that we looked at. So the number that it can reach, in this case number 6, means that we have an 8, at least an 8-bit, 8 values in the palette. And that's how you draw a screen. It's like paint by numbers. This is how the Atari Lynx does it, because it has 16 color availability out of 4,096 that you can choose. Audio is kind of weird because you compute the audio by looking at the volume. So every period of the frequency of your sound, the volume shifts a bit, and you get a pattern like you see here. And that is the distinctive 8-bit sound, because it's 256 discrete values, so it has a sound to it. And if you do a sawtooth thing, or a block, a square wave, or maybe noise, it's like percussion, you can build all these typical instruments that you know from, for example, the Commodore 64. Some other things that I learned building this. Sometimes you want to look at a bit of memory, and you want to look at it in 2 ways, because sometimes you say, okay, I've got 2 bytes, I want to know the low and the high byte, but sometimes I want to see it as a U-short. So this is kind of how you can say I have a struct layout, but it's like a double mapping. The field offset 0, that's where we start reading memory, and that's the U-short value. But if I ask for low byte, or maybe high byte, I get the second byte in the bit of memory there. So you've got like 2 ways to look at a bit of memory. Another way that you things that you might do is looking into ways to work efficiently with endianness. Because if you have a big or little endian, it matters in which order the bytes of the U-short are. It's usually little endian, but a file format or network protocol might do it differently. So you can look at the is little endian of the bit converter. It's a thing that you might not have encountered in normal programming, but that tells you your machine which endian does it have. And you can either use bit converter 2U in 16, which is the one that uses the thing you just asked. So it means little endian, if it's little endian, and otherwise you need to compute it yourself. You could also say you always take the bottom line, because then you're safe. But there's even other ways of doing this. So this doesn't compile, but look at the way, if you have memory, you can use spans and slices to pick the 2 bytes without making a copy. So this is extremely efficient. And the Marshall get array data reference and the unsafe add are underneath span of t. So it's actually ripped out in what I showed you earlier, but span of t does the same thing. And there's also binary primitives that allows you to specify read it in little endian or big endian. So if this becomes a thing, more modern libraries like system memory they do have additional things to work with the byte level of memory. All right. I also found that if you do debug right line, because poor man's debugging, just output those things, your emulator slows to a halt, even if you do the right line if. So like I'll turn it off, but because it's millions of iterations, there is string building involved. It just it doesn't go well. All right, I'll skip the gaming frameworks because we're out of time. But this is an ongoing journey, building this thing. We've looked at a number of things on how we get the emulator core running. There is a new level to this. You can even go inside of instructions and do the individual cycles of where you see the data is being fetched, almost like we did, but much more detail. I think it would be really cool to have debug support, so you can do debug breakpoints inside of the 6502 code, so you can inspect the code, do disassembly, and have an abstraction on top of that with instructions and opcodes, those kind of elements. And I've got inspired by an architect at Microsoft who built an emulator with an MCP server inside. So the MCP server has tools, the way you express what an MCP server can do, to set breakpoints, to disassemble code, and to analyze it. So you could use something like Claude or a language model that is capable of understanding code, the 6502 code, and it can communicate with your emulator and start analyzing a game or your own emulator and deduce or reverse engineer what code was that you didn't write yourself. So amazing things, because the LLM will say, okay, I'll put a breakpoint there and I'll run to that, and oh, I see that this is executed directly after the V-blank of building the screen, and now we look at the value of a controller. And then it can, build up reverse engineered code that is commented, can find bugs in your code or weird things. Well, anyway, super, super cool. I hope that in this past hour, you've got a bit of an idea of what it means to build a game emulator. Managed code, very doable. It's not that, 4 megahertz, that's quite achievable. You'll probably learn a lot about working at the byte level instead of business logic, for example, different thing. You have the modern memory management, span of T, memory of T, read-only sequence, the different ways of building high-performance code. I found it very interesting to do so. I encourage you to go write your own or look at the code of emulator implementations that are already out there if you are interested in this. That's it for now. There's some resources here. You'll get the slides, but you can look at those things. I encourage you to go and restore these things, because the image that I removed, that was emulators. Consoles don't die, they get emulated. So it's for prosperity, I guess. Thank you very much, and enjoy the party.